Okay, so let's start. So, my name is Revant, and I will be your teacher for this course, Theory of Computation and Compiler Design, for all three sections of your Sem 6 CSE batch. So, this is your course details page, CUCS 1008, Theory of Computation and Compiler Design. So, compiler design. So, what are compilers? So, compilers, every programming language has their own compiler. A compiler is basically a program that takes your code that you have written and generates executables from that. So executables or binaries or whatever, that something that is basically a series of machine instructions that can be executed. So for C we use GCC, for C++ we use G++, for Python we use the Python interpreter, and for Java we use Java C compiler that will generate the Java bytecode that will run on Java virtual machine later. So compiler basically converts your code that you have written in that language into executables fundamentally. So every language ships with their own compilers written by whoever created those languages. And since all languages are different, every language has their own compiler. So yeah, so basically that's what compilers are. But so before we first create languages and develop compilers, we first need to basically understand what is a language, right? So how we can formally define and describe a language. It is very important that we first define the language formally, because programming languages are they are very strict compared to like normal human spoken languages, right? So human languages we can, like for example English or Hindi or Telugu, we can just speak and like change the tone and slang or adjust some words, create new words, and people will still understand, right? We have grammar rules for every language, but in spoken language they are not very strict. Even if we deviate from those grammar rules a little bit, people will still be able to communicate and understand. But programming languages, they are completely run in computers, interpreted by computers, so they have to be perfectly defined, right? All the grammar rules, how we define a language, we first need to understand that part. So yeah, so theory of computation basically deals with that, how we can formally define a language, what must be given as a part of a language's description, a language's grammar rules. And for different classes of languages, we will see in theory of computation, we will see how to build machines that understands these languages, or like machines are basically, in computer they are programs, but not exactly. We will see what the definition of a language is, what the definition of a machine is, a definition of a computational problem in theory of computation. And we will also see in theory of computation like what it means to say something is computable, and we can only describe languages or problems that are computable, right? So we will define what it means to be computable. I mean, not exactly define, but we will see. So yeah, compilers are basically converts your program into executables, and theory of computation gives all the theoretical foundations that we need to understand and develop these processes. Yeah, so theory of computation again has mainly three topics that provide the fundamental mathematical basics for compiler design, and compiler design has basically six stages of compilation that we will see, and we have a total seven modules. So every module will cover each stage of compiler design, and every module also includes the prerequisite from theory of computation part. So basically every module contains some part of theory of computation and some part of compiler design stage, right? So seven modules, and we will not do any of experiments. This is a complete theory plus practice course, no practicals, and we will see the syllabus in detail in a few minutes. Okay, so again, these are the textbooks that we will follow. This is for the theory of computation part, and this one is for the compilers part. So you can search these textbook names in online, and you can find the PDF versions easily. Yeah, and for compilers part, this textbook is actually available in your library, so go check it out. Yeah, we will start now. Okay, so now let's have some basic discussion about compiler design and syllabus. Yeah, so a compiler takes your code or the program you have written and generates machine instructions or executables, or we can call binaries. Or in the case of Java, they generate bytecode. In case of Python, they are just interpreted, no executable generated. So in C, you have this is the compilation phase, gcc proc.c, and this is the executable you will get. So this does not need any virtual machine like Java. It will, this is the compilation for every class in the Java file. It will generate separate .class file, which is what we call bytecode, and we run that bytecode on the Java virtual machine. So here to run we need a runtime environment. In this case we call it just Java. In C they generate direct system binaries or system executables. In Linux they generate ELF files. In Windows, PE files, portable executables. In Mac OS they generate Mark-O binaries, something. So C language will always generate direct system level binaries. That is very different from Java bytecode, we will see in class. Yeah. So in Python is completely different. It is an interpreted language, so there is no compilation phase. It is interpreted. Every line is read and executed at the war series in line by line. So there is no executable generated. The Python file itself will run on the Python virtual machine or like Python environment, whatever. So all the languages are different, all the architecture details are different, but in this course we will mainly focus on how the language, all the code you have written is parsed, some basic, all the basic things you need. Besides these architectural decisions and differences, we will mainly see the basic building blocks of a compiler, right? All the basic stages in understanding a language before generating the executables, right? So this is your compiler. At the top it will take your code, and at the bottom it will give out machine instructions or executables or binaries, right? So these are the intermediate stages of how your code passes through different stages before it finally generates the executables, because compiler and compilation is not a simple process, it is a complicated process with all these different stages, right? So first it will go through a stage called lexical analysis. This is basically identifying words. Simple explanation is just it identifies words, and in this context we call them tokens actually. So this stream of tokens in your code, they are identified and sent to syntax analysis phase, which is basically identifying sentences, basically. And then semantic analysis, this group of sentences, they will be arranged in a tree structure, and semantic analysis will look at the tree and add some type different type checking, like in C we have int or char or float. It will add type definitions to your individual variables and assigns meanings to these statements, basically. So after assigning meanings, we have a meaningful tree representation of our code. So that will be sent to this stage. This is basically ICG, intermediate code generation, and it will finally convert into intermediate representation, which is basically not your machine language instructions. It is some intermediate representation. We will use this intermediate representation because we need to optimize our code first. So that's why we will do that in an intermediate representation and then convert into machine instructions, right? So from these meanings assigned sentences, we will first convert into intermediate representation using this stage called intermediate code generation, and then these series of instructions are optimized a bit and then sent to this stage. This is basically target code generation, and this will output the machine instructions or executables, and before releasing they will be optimized a bit further, and at the end we will receive our final executables, right? So we will discuss through each of these individual stages. Okay, so we will continue in another. Okay, so another thing I want to add here is basically theory of computation will have these three main topics, like the three main modules from theory of computation. So this part will lexicon analysis will use heavily this part, regular languages, and the machine constructions in regular languages is used to implement lexicon analysis mainly, and syntax and semantic analysis phases, they both use context-free grammars part very much, and Turing machines part is not used in compilers. This is just a theoretical concepts, right? And these will mostly deal with, these are basically like Turing machines are the most powerful computational machine models, right? So we will see what these are individually and what these all represent basically. Okay, we will see in next video. So now let's just have a brief general discussion, okay, about like history of computers, history of CPUs, programming languages, and how they evolved, the timeline basically. So like before 1940s or 50s there were no CPUs basically, right? Like currently we have Intel or AMD, or for MacBooks we have Apple Silicon chips. For mobile phones we have like Snapdragon, MediaTek, whatever CPUs, right? So currently most of us use like Intel i5 or AMD Ryzen 5 CPUs. So they are basically 64-bit CPUs, right? Like Intel or AMD, they use 64-bit processors. So what are they like? So you have a CPU, the chip, and it has like all these pins around in all directions, or like currently like on the chip itself they have like this 64 pins popping out of this plane. So you physically insert it into the motherboard. It has like 64 holes this CPU will go right here. So 64 pins into 64 holes. These are like normal current day chips. So how these 64-bit chips work is basically we give a instructions, series of instructions, right? They are all 64-bit instructions. Instructions are basically like, and again we have currently 16 registers. Registers are like basically some storage options, right? Like, so we have 16 units of storage that we call registers. These are like temporary variables, or like temporary variables that are physically on the board. Again, each are 64-bit registers. They can hold 64 bits of information. So all these instructions are basically like add R1, R2. What this does is, in register 64-bit we have right R1. R1 will become R1 plus R2. So it will add the 64-bit contents of both R1 and R2 and put it in R1. So this is an example of one basic instruction. And another instruction can be like move R1, R2. So what this does is basically R1 will be replaced by contents, the 64-bit content in R2. So whole computers, whole operating system, all the software, all computer software, including our Windows OS, the bootloader, everything is basically a series of these small 64-bit instructions. So these are modern day computers. This is the CPU, heart of the computer, running all the 64-bit instructions in series that it gets. So currently we have like our processor like some gigahertz or some megahertz. You heard of these numbers, right? So like I don't remember exactly, but some giga is some 10 power 6, mega is some, no, giga is 10 power 9, mega is 10 power 6. So these many instructions it can run per second. These small amount of instructions, 10 power 9 or 10 power 6, these many instructions per second it can run. So we have that much faster computers, CPUs basically. So they are what machine instructions basically. So currently we have these kind of processors, but in before 1940s, during those ages, we did not have the luxury of these kind of processors, right? So all those processors are basically huge supercomputers. They are made using physical transistors, and all these instructions, they are passed by like manually turning on and off switches. Like they will set a 64 16 or 8-bit instructions, right? So for those 16 or 8-bit instructions, they will use 16 switches. So turning on or off, they will set 0 or 1. After adjusting all the 16-bit switches, they will send that instruction to the CPU. That's how earlier programs were executed, very manual, very slow. But they formed the foundations for our modern day computing, right?
So eventually CPUs evolved. We currently have integrated chips, right? Very fast. So slowly the chips evolved, and people are writing programs in still machine language, right? They write 16-bit or 8-bit zeros and ones and series of those as the programs, all machine instructions. So after that, sometime they realized that they have to write in a better way. So that's how they started creating programming languages. So the idea is to like write a write your program in a programming language and compile it, so that will become your machine instructions. Now you don't have to write machine instructions by hand anymore, right? You can just write your program in your programming language, and the compiler will convert it into machine instructions. So that's how the compilers are born. And many books will say Fortran 1 was the most first ever programming language, but it is just first ever commercial programming language many people used. But there are some small projects, small languages existed at the time. I think this came out in 1957. They started work creating this language and writing compiler in 1955, and in 57 they released this compiler and this language. So this is like some history of how computers and compilers, CPUs evolved. So now that they have a language to write software. So before, when they wrote compiler for the Fortran language, compiler for this language, they didn't have any software like we have. Like we can write a compiler currently we can write a compiler in C program, or we can write a compiler using Java language. But at the time they wrote this compiler using machine instructions only, written by machine instructions. But later, after they wrote compiler for this language, they now have a compiler. So now if they want to add any modifications or changes to the Fortran language, they need to write a new compiler. So the next version of this compiler, it is written in this language itself. You understand? Like they now don't have to write in machine language instructions anymore for the next version of compiler. For writing the next version of compiler, they can write in the current version language and compile it using current version's compiler. It will automatically generate a compiler executable for the next version. So after like initial compilers and initial programming languages started evolving, programming everything became simpler, very simpler. Like they can write operating systems now. Earlier they didn't even have any operating systems. Everything was basically directly run on CPU, right? So that's how whole computers, programming, everything is revolutionized, right? So I just wanted to give you this basic history. Okay, so now we will stop here, and from the next video we will continue from basics of theory of computation and start with some basic terms and definitions. Okay.